Hello. Over the last few weeks, we have discussed the expression shown on this slide at length. This expression tells us that the expectation for the sample mean, left-hand side, for a set of n identical random variables has the same value as the expectation of the random variable, the quantity that is on the right-hand side. In our studies of the variance in the weeks before last, we discussed why we prefer to use large numbers of data points when we calculate sample means. We found that the estimator of expectation that we get by computing a sample mean from a small number of data points is an accurate but not precise estimator for the expectation. If, by contrast, we calculate a sample mean from a large number of data points, we get an estimator for the expectation that is both accurate and precise. It is important to note, however, that the sample mean is always a random variable. We cannot eliminate the randomness in its value by calculating a sample mean from a large number of experiments. Why, you may ask, is it important to note this? Well, let's suppose that Alice and Bob do the same experiment. They complete their experiments independently and then compare the results they obtain. Alice confidently asserts that the mean was equal to 5. Bob then shoots her down by noting that the mean in his experiments was 4.2. After discussing what they did, Alice and Bob cannot work out what accounts for the difference in their results. As far as they can tell, the experiments they did were identical, so they should have got the same result. They thus go and ask the professor who is teaching the module. The professor then tells them that they shouldn't simply compare the final results. They should compare the distribution of results they obtained in the experiments. What Alice and Bob's professor is suggesting here is a very neat trick for making sense of the results of experiments. In practice, neither Alice or Bob, or any researcher for that matter, can control all the factors that might affect the result of an experiment. Researchers thus control the things they can control and use a mathematical model to describe the randomness that is introduced by factors that the researchers are not controlling. For example, let's suppose that Alice and Bob were investigating the rate at which a chemical reaction occurs in solution. The principal things that affect rates of reactions are the concentrations of the reagents in the solutions and the temperature. Alice and Bob might therefore be confident that the temperatures and concentrations in their two experiments are identical. Small differences in the way that the solutions were stirred in the two experiments that Alice and Bob performed might, however, lead to differences in observed rates, even though the temperatures and concentrations are identical. These factors that are not under the experimentalist's control ensure that even if Alice does the same experiment twice, she might not gain the same result twice. The solution, then, is to quote multiple results and to thereby characterize the randomness that is induced by the factors that are not explicitly controlled within the experiment. The simplest way to characterize the randomness is to use a method known as resampling. In this method, you simply calculate the mean multiple times. You then have multiple samples from the distribution for the mean and can thus characterize the distribution for this random variable using all of the methods of calculating statistics that we have learnt about in this course. This perhaps sounds complicated, but it really isn't. a Python program as simple as this one can be used to resample a sample mean. As you can see here, I have generated uniform random variables here and added n of them together. The function at the top of this slide is thus a function for generating a sample mean from n uniform random variables. This function can then be used just like the functions we have written for generating uniform, Bernoulli, binomial, geometric, negative binomial, and all the other types of random variables that we have encountered within this course. This is precisely what is done in the code at the bottom of the slide. As you can see, I have a for loop that calls my function for generating a sample mean multiple times. I can thus fill this numpy array called samples with 100 samples of a sample mean computed by adding together 10,000 uniform continuous random variables. This array of samples is then just like any other array of samples that I generate from a random variable. I can thus calculate a mean from this data, I can calculate a median, or as shown here, I can calculate the 5th and 95th percentiles of the distribution. The net result of resampling is that Alice now has a way to compare her results with Bob's. By resampling, she might note that 90% of her samples were between the 5th and 95th percentiles of her distributions of sample means. For her resampling data, she might note that these percentile values were 3.5 and 5.5. She then notes that Bob's result is within this range that she observed, and it is thus likely that the experiments performed by Bob were sampling the same distribution. To summarize then, what we have found in this exercise is that it is massively important to provide information on the distribution that was sampled when we describe the results of experiments. You should not simply quote the average result as the final result. When the distribution of random error is not characterized, it becomes impossible for other researchers to reproduce your results. It is, however, sad to say that reproducibility is a massive problem for many research papers that are out there. Don't let your work be one of these papers. Learn how to calculate these errors by completing the next few exercises and then make sure you consider how you are going to do this whenever you write a report where you are sampling from some distribution. Thanks for your attention and good luck with the exercises.